Hello guys, welcome to our channel FebTV Sri Lanka. So in this video, I am going to talk about structure of matter science chapter 3 and this is part 2. First of all, if you are new to this channel, consider subscribing and if you need, you can always unsubscribe later. Enjoy. So this is part 2 and let's start from metals, nonmetals and metalloids. This is the periodic table and blue color ones represent metals, yellow, orange color ones non-metals, noble gases, brown color ones, and these are metalloids. The elements written in blue in the boxes on the left hand side of this pattern are metals. The elements indicated in brown on the right hand side are non-metals. The elements indicated in light green around the steps have properties in between the metals and non-metals. Therefore, they are called metalloids. So these green ones are metalloids because they have features of both metals and nonmetals. So let's discuss about metals first. Of the elements identified so far, more than 80 are metals. In nature, these exist as native metals as well as compounds of metals. Metals such as silver and gold are found as native metals in nature, whereas many metals such as iron, aluminium, magnesium and sodium exist as their compounds. Silver and gold are native metals and iron, aluminium, magnesium, sodium are examples for compounds. Physical properties of metals have a metallic luster. Luster means having a shiny surface. Sonorous, giving a ringing sound when struck. Exists in solid state at room temperature. Mercury, though a metal, is a liquid. This is the only metal which is liquid at room temperature. Mercury. Malleable, can be hammered into sheets, and ductile means can be drawn into wires. Good conductors of heat and electricity. Generally have a high density. Chemical properties of metals. We discussed physical properties of metals and now chemical properties of metals. Metals form positive ions or cations by losing electrons. Another name for positive ions is cations. They combine with oxygen to form basic oxides. The oxides, when dissolved in water, form basic solutions. Our first element is sodium. Sodium is a metallic element belonging to group 1 of the periodic table. It is a highly reactive element. It never exists as the native metal. Because of its high reactivity, it exists only as compounds. Sodium chloride, the main compound containing sodium, occurs in seawater. Sodium chloride means common salt. Sodium metal is stored in paraffin oil or kerosene so that it does not come into contact with air. When sodium metal is taken out of paraffin oil, its luster or shiny surface disappears. Physical properties of sodium. It is a soft metal which can easily be cut with a knife. It floats on water because its density is less than of water. It is a conductor of heat and electricity. Chemical properties of sodium metal. Sodium shows a high reactivity towards oxygen and it reacts rapidly with oxygen in air to form the oxide of the metal. Sodium metal vigorously reacts with cold water forming sodium hydroxide and hydrogen gas. It reacts violently with dilute acids and forms salt and hydrogen gas. Since this is extremely dangerous, you shouldn't attempt this. Uses of sodium. Production of sodium cyanide used in the extraction of gold and silver. Making sodium amalgam which is used as a reducing agent in organic chemistry. Extraction of metals such as titanium, zirconium from their compounds. Production of indigo dye used to dye trouser materials. Denim, used in the production of street lamps with a yellow glow. Our second metal is magnesium. Magnesium is a light reactive metal. It does not exist as the native metal in nature. In seawater, it occurs as magnesium chloride. When exposed to air, magnesium tarnishes so its luster cannot be seen. But when cleaned with a sandpaper, the luster becomes visible. Physical properties of magnesium. It is a good conductor of heat and electricity, has a higher density than that of water. Uses of magnesium. By mixing magnesium with aluminium, an alloy called magnesium is produced. This alloy is strong and resistant to corrosion. It is used in aircraft industry and in making parts of automobiles. Production of medicines, example milk of magnesia, used as metal that prevents corrosion of iron. Okay guys, now let's talk about nonmetals. Bromine is a liquid at room temperature. Chlorine, fluorine, nitrogen, oxygen are some nonmetals occurring in gaseous state. Nonmetals do not have a metallic luster. They cannot be hammered into sheets or drawn into wires. That means they don't have the property malleable and ductile. Many nonmetals are brittle and are poor conductors of heat and electricity. However, graphite, a nonmetal, is a good conductor of electricity. Nonmetals have a relatively low density, but the density of diamond is high. Chemical properties of nonmetals. Nonmetals form negative ions, anions. Many oxides formed by nonmetals with oxygen are acidic. Mostly these exist in the gaseous state and they easily dissolve in water and form acids. Nitrogen. Nitrogen exists as a free and diatomic gas in the atmosphere. About 78.1% by volume in the atmosphere is nitrogen gas. Nitrogen is also present as a component in animal and plant proteins. Nitrogen also exists as a constituent element in soil air, in organic substances such as humus and nitrates, nitrites and ammonium compounds. Physical properties of nitrogen. It is a colorless and odorless substance and it is lighter than air and is slightly soluble in water. It is a gas of very low reactivity. Nevertheless, at high temperatures, nitrogen gas reacts with nonmetals such as oxygen, hydrogen, carbon and silicon as well as metallic elements such as magnesium and aluminium. When sent through a strong electric arc, nitrogen combines with oxygen in the atmosphere to form unstable nitric oxide gas. The nitric oxide gas so formed reacts further with oxygen in air to form an acidic gas called nitrogen dioxide. During lightning, this process occurs naturally. Chemical properties of nitrogen. Nitrogen is a non-supporter of combustion. Under special conditions, nitrogen gas reacts with hydrogen gas to form ammonia gas, NH3. Industrially, ammonia is manufactured by this method. Ammonia so prepared is used as a raw material to produce nitrogen-containing fertilizers and explosives. When heated, nitrogen gas reacts with metals like magnesium to form metal nitrides. Uses of nitrogen. Nitrogen gas is used to produce ammonia in industrial scale chemical fertilizers and other nitrogen compounds. Since it is an inert gas, it is used to fill electric bulbs and thermometers. When making electronic devices, a nitrogen gas environment is used. When stored in some substances, nitrogen is used as a blanketing gas. When packaging milk powder, nitrogen is used. Liquid nitrogen is used as a coolant. It is also used to fill vehicle tires. Sulfur. Sulfur is an element that exists in different forms in nature. Those forms are referred to as allotropes. Sulfur occurs in crystalline form as a yellow brittle solid and in amorphous form as a white powder. In nature, it is found both as a native element as well as compounds like sulfates and sulfides. It is a constituent element in some amino acid found in the bodies of living beings. Physical properties of sulfur. Sulfur burns with a blue flame in air and forms sulfur dioxide gas. When heated with sulfur, many metals form the metal sulfide. Uses of sulfur. Sulfur is used to produce sulfuric acid, vulcanize rubber, and make calcium and magnesium sulfides, which are used to bleach wood pulp. It is also used to produce paints containing sulfide solvents like carbon disulfide, sulfur dioxide gas, matches, crackers, and gunpowder. Sulfur is also used in the production of wine, beer, and medicines and is used as a fungicide. Carbon. Carbon is a nonmetal element occurring in abundance. It occurs as carbon dioxide gas in the atmosphere, animal and plant tissue, all organic compounds, coal, petroleum products, and other hydrocarbons containing carbon. It is an element showing allotropy. Carbon has crystalline forms as well as amorphous forms. In crystalline forms, atoms are orderly arranged, but in amorphous forms, there is no such arrangement. Physical properties of carbon. Physical properties of carbon differ according to the allotropic forms of carbon. Except diamond, the other forms of carbon are black in color and exist in the solid state. Their density is relatively low, but diamond is the form with highest density. Diamond is much valued because of its high reactivity index and hardness. Diamond is a poor conductor of electricity, but graphite is a good conductor of electricity. Charcoal has the ability to absorb gases. Chemical properties of carbon. Carbon is an element of low reactivity and it combines with oxygen at very high temperatures but does not react with substances like acids, bases, and chloride. Amorphous forms like charcoal reacts chemically. When strongly heated and ignited, charcoal reacts with oxygen to form carbon dioxide. At high temperatures, carbon reacts with calcium oxide forming calcium carbide. Forms of carbon and their uses. Amorphous carbon, production of black color ink and vulcanizing rubber. Coal, the use as a fuel. Graphite, making pencils, making electrodes of electrochemical cells, used as a lubricant. Diamond, making jewelry, cutting glasses and gems, used as pivots at points in machines that are subjected to wear away. Charcoal, absorbing gases and purification of water. Carbon fibers and carbon tubes, used to produce wood reinforced by nanomaterials. Carbon fiber is very light and it is very strong. Let's talk about metalloids. Our first metalloid is silicon. Except oxygen, silicon is the most abundant element in the Earth's crust. As compound, silicon occurs in both crystalline and amorphous forms. Quartz, sand, and gems such as emerald are crystalline silicon compounds. Clay is an amorphous silicon compound. The melting point of silicon is 1410 Celsius. Uses of silicon. Used in making transistors and diodes, used in making solar cells, and used in making computer equipments. Boron. Pure boron occurs as a black crystalline solid. It melts at 2200 Celsius degrees and has a high density of 3300 kilograms. Its reactivity is relatively low, therefore it does not react even if heated to high temperatures in air. At very high temperatures, amorphous boron reacts with substances like oxygen, nitrogen, nitric acid, and concentrated sulfuric acid, carbon and sulfur to form the corresponding compounds. Uses of boron: used in welding metals, used in making skin cream, used in making glass that can be heated into high temperature. Acidic, basic and amphoteric nature of oxides. Elements in period 3 and oxides. Acidic and basic nature of the oxides. Elements in period 3: sodium, magnesium, aluminium, silicon, phosphorus, sulfur and chlorine. This is sodium oxide and this is magnesium oxide, aluminium oxide, silicon oxide, like that. And sodium oxide is strongly basic, magnesium oxide is weakly basic, aluminium oxide amphoteric, very weakly acidic, weakly acidic, strongly acidic and very strongly acidic. Acidity of the oxides increases as basicity of the oxide decreases. It is like this. Basicity decreases for this side and acidity increases. Very weakly, strongly and very strongly. This side strongly, weakly and amphoteric. Amphoteric means elements that have features of both basic and acidic. When the oxides of elements in period 3 are considered, there is a clear pattern in the variation of their acidic and basic properties. The oxide of sodium, which is on the left side of the period 3, is strongly basic and magnesium oxide is weakly basic. From silicon to chlorine, the acidity of the oxides increases. Aluminium oxide shows both acidic and basic properties. Such oxides are called amphoteric oxides. Accordingly, from left to right of a period in the periodic table, the basicity of the oxide decreases and their acidity increases. Chemical formulae. Our topic is valency. The combining ability of an atom of an element is known as the valency. This is measured relative to hydrogen. Accordingly, the valency of an element is either the number of hydrogen atoms which can combine with or can be replaced by an atom of that element. The valency of an element is equal to the number of electrons lost from or gained by an atom of that element or the number of pairs of electrons shared between the atoms during chemical combination. We know that chemical symbols are used to identify elements easily. For carbon it's C, potassium it's K, K means kalium. K means kalium. This is sulfur and calcium Ca. Similarly, chemical symbols are also used to signify chemical compounds with each. For instance, H2O is used to represent water, a compound consisting of 2 hydrogen atoms and 1 oxygen atom. This is called the chemical formula of water. If there is a number at the bottom of the symbol of an element in a chemical formula, it indicates the number of atoms of that element present in a molecule of that compound. If there is no such number, only one atom of that element is present in molecule of that compound. Writing formula using valency. Compounds are formed by the attachment of atoms or ions of elements by chemical bonds. Therefore, to write the formula of a compound, their combining powers or valency should be known. The formula is written so that the respective combining powers are balanced. The valency of hydrogen is 1. The valency of oxygen is 2. So 2 hydrogen atoms can be combined with 1 oxygen atom. This is written as H2O. The valency of nitrogen is 3 and hence 3 hydrogen atoms can be combined in one nitrogen atom. This is written as NH3. NH3 means ammonia. H2O means water. And the valency of carbon is 4. So 4 hydrogen atoms can combine with one carbon atom. This is written as CH4 and CH4 is methane. Let's write it down. Water, ammonia, and this is methane. So what is done in writing the chemical formula of a compound is connecting the atoms so that their combining powers become equal. This is done by exchanging the valencies of the two elements and writing them at the bottom and on the right hand side of the respective symbols. So let's try some examples. Let's write the chemical formula of sodium chloride. Sodium means the symbol of sodium is Na, and chloride, the symbol of chloride is Cl. So the valency of element sodium is 1 and the valency of element chlorine is also 1. So if we exchange these valencies, we can get it as Na1 Cl1, but we don't need to write these ones because they are just equal and it is not essential, so we can finally write it down as NaCl, chemical formula for sodium chloride. Calcium chloride. The chemical symbol of calcium is Ca and Cl. Valency of calcium is 2 and valency of chlorine is 1. So if we exchange these two valencies, we can get it as Ca1 and Cl2. So if we write down it finally here, CaCl2. This is the chemical formula for calcium chloride. Sodium oxide. Chemical symbol of sodium is Na, oxygen, and the valency of sodium metal element is 1 and oxygen is 2. So if we exchange these valencies here, Na2O1, finally write here Na2O. Chemical formula for sodium oxide. Okay, let's try calcium oxide also. So the chemical symbol of calcium is Ca. Chemical symbol means scientific symbol. Oxide, oxygen. So the valency of calcium is 2 and oxygen is also 2. If we exchange those two, Ca2O2, we can cut these 2's because they are same in number. So cut these 2's and write it finally here, CaO. The chemical formula of calcium oxide is CaO. This is our final topic in this lesson and it is polyatomic ions, radicals. A polyatomic ion is an orderly arranged group of atoms of elements with a charge. So guys, this is the end of our chapter 3 in science structure of matter, and if you have any problem, leave a comment, and if you like this video, put a like and don't forget to subscribe. So bye bye.